One last thing before we leave the solar system generally. How long ago did it form? Well, we get the answer to this by using what's known as radiometric dating. If you've ever heard of carbon dating before, that is one type of radiometric dating. The idea is that there are certain isotopes that are radioactive. If you remember back, an isotope is an atom that has the same number of protons but differing numbers of neutrons. So it's the same element, but because it has differing numbers of neutrons, it might behave very slightly differently. Well, some isotopes are radioactive. What this means is they will spontaneously change from what they are into something else, usually by giving off harmful radiation. This starting isotope is what we refer to as the parent, and then what it turns into is what we call the daughter. One way we can characterize how long it takes for our sample to decay is by looking at the half-life. The half-life is the amount of time that it takes for half of the sample to decay, for half of the parent to turn into the daughter. Well, the idea is that if we know a sample's half-life, we can then compare the ratio of parent to daughter isotope to figure out how old the sample is. So, for an example, in this graph, we are looking up and down at the percentage of potassium-40 to argon-40. Potassium-40 is the parent, and it turns into argon-40, the daughter. So at the very beginning, we have all potassium and no argon. This shows that we've gone through absolutely no time yet. There's been no change. However, as time progresses, potassium turns into argon. So the amount of potassium decreases and the amount of argon increases. After one half-life, we'll have half potassium and half argon. So if we have a ratio of 50-50, we know it's gone through exactly one half-life. As we continue, the amount of potassium continues to decrease and the amount of argon continues to increase. So what we can do is we look at the ratio of argon to potassium, and that will tell us how long this process has been happening. If there's lots and lots of parent isotope, then the sample has to be very young. If there's 50-50, we've gone through exactly one half-life, and if there's lots and lots of daughter and very little parent, then we know that it's a very old sample. It's not just gone through one half-life, it's actually gone through many. How different isotope systems have different half-lives, meaning that they're going to be useful over varying ranges. So again, as an example, we can use carbon. This is what is used for carbon dating. Specifically, we look at carbon-14. Carbon-14 turns into nitrogen-14 with a half-life of 5,730 years. So if we've gone through one half-life, then we'll have 50% carbon-14, 50% nitrogen-14, and we know that the sample is around 6,000 years old. Now, because of how long this half-life is effective, that means that we can use carbon dating from around 100 to about 70,000 years. In other words, it's going to be really, really good for archaeology and anthropology, but it's not going to help us determine the age of the solar system. Other systems, we have potassium-40 and argon-40, which we just looked at, with a half-life of 1.3 billion years. Uranium-238 to lead-206 with a half-life of 4.5 billion years, and rubidium-87 to strontium-87 with a half-life of 47 billion years. Because these systems have half-lives in the billions of years, they're going to still be around, even with how long it's been since the solar system formed. So we look at these different systems then in as many different samples as we can get. So we have the oldest Earth rocks we can find, we have moon rock samples from the moon missions, we even have meteorites. As we look at the ages that we get from radiometric dating for all of these things, they all point towards the solar system forming about 4.5 billion years ago. This is a number that I highly recommend you know. The solar system is about 4.5 billion years old. Alright, here's our 5th lecture quiz question. A sample of material shows it has very little daughter isotope compared to the parent isotope. In other words, we have very little daughter and lots of parent. Therefore, the sample A is very old, B has gone through only one half-life, C has gone through several half-lives, or D is very young. Go ahead and think about it, and we'll discuss in just a second. All right, so if we have just a little bit of daughter and lots of parent, that means we haven't even gone through one half-life yet. In other words, the sample has to be very young. So the correct answer is D.